In this video, I'm going to show you how we can use calculus methods to solve optimization problems. Let's start with a simple question. Find two numbers whose sum is 20 and whose product is maximum. So here we are looking for two numbers, say x and y, whose sum of those numbers, x plus y, is 20, but we want the product, the multiplication of those numbers be maximum. There are infinite pairs of numbers whose sum is 20. For example, 1 and 19, 2, 18, 5, 15, 7, 13, 10, 10, 0, 20, -5, 25, and so on. The sum of all of these pairs, if you check, is 20. 1 plus 19 is 20. 2 plus 18, 20. 5 plus 15, 20. 7 plus 13 is also 20. 10 plus 10 is 20. 0 plus 20 is 20. -5 plus 25 is also 20. But if you check, the product of these numbers are different. 1 times 19 is 90. 2 times 18 is 36. 5 times 15 is 75. 7 times 13 is 91. 10 times 10 is 100. 0 times 20 is 0. -5 times 25 is -125. By looking at this table, we can see that maximum of the product happens when the two numbers are equal and they equal 10. And the product, the maximum product, is 100. So the two numbers whose sum is 20 and the product is maximum is when the two numbers are 10 and the product of those numbers is 100. But how we can prove this with the calculus methods? We are looking for two numbers like x and y such that x plus y will be 20 and the product of these two numbers, x times y, will be maximum. So we want to maximize the expression x times y. If you remember from calculus, for maximizing or minimizing expressions, we have to find the critical points. But for finding critical points, we have to have one variable in our function. But here, the product is in terms of x and y. So we have to try to rewrite this product in terms of only one variable. That variable can be x or y, but we have to make it only one variable. To do so, we can use our constraint that here we have. We know that x and y, the two numbers, are related by this equation. X plus y is 20. So we can use this relation to find one of the variables in terms of the other one. For example, if we keep y in the left side of the equation and we move x to the other side of the equation, y is 20 minus x. Now if we replace in our product y with 20 minus x, the product can be written as 20x minus x2. If we multiply x in the bracket, we get 20x minus x2. Now we can use derivative for finding critical points. For finding critical points, we have to find derivative of the function. Derivative of 20x is 20 and derivative of x to the 2 is 2x. If we set derivative equals 0 for finding critical points, from this equation 20 equals 2x, which we get x equals 10. So one of the numbers that we are looking for is 10, and for finding the other number we can plug in this 10 in this equation for finding y. Then y would be 20 minus 10. 20 minus 10 is 10. So y is also 10. So the numbers whose sum is 20 and the product is maximum are 10 and 10, which confirms the result that we get from our table. And note that the product of these two numbers is 100. 10 times 10 is 100. Let's do another example. Find two positive numbers whose product is 100 and whose sum is minimum. We want to find two numbers. Let's name those numbers x and y. The product of these two numbers is 100. This is the constraint that here we have in this question. The relation between the variables is that x times y is 100. And the sum of these numbers we want to be minimum. We want to minimize the sum of these two numbers. If we show sum with s, s would be x plus y. We want to minimize x plus y. For minimizing s, we have to rewrite s in terms of one variable. To do so, we use our constraint to find one variable in terms of the other. If we divide both sides of our relation by x, y is 100 over x. So we can write s as x plus, instead of y, we write 100 over x. So now our function is in terms of variable x, and we can use derivative to find the minimum of this function. For finding minimum, we have to find critical points. So first we have to find s prime, derivative of s. Derivative of x is 1, and derivative of 100 over x, if we use quotient rule, is derivative of the top is 0 times the bottom is 0 minus derivative of the bottom is 1 times by 100 is 100 all over bottom squared. So derivative of s can be written as 1 minus 100 over x2. The other way that you can find derivative of 100 over x is to bring x to the top and write it as 100 times x to the negative 1. Then use power rule to find derivative. For finding derivative of 100 times x to the negative 1, we can bring the power down. If we bring negative 1 to the front, negative 1 times 100 is negative 100 times by x to the power of negative 2. We have to subtract the power by 1. And negative 100 times x to the negative 2 is negative 100 over x2. Note that because the power is negative, we can bring x to the negative 2 down to the denominator, and it is x2. This is the other way that you can find the derivative of 100 over x. Now for finding the critical points, we have to set our derivative equal 0. 1 minus 100 over x2 equals 0. For solving this equation, you can do a common denominator, or you can multiply both sides of this equation by x2 to get rid of x to the 2 in the denominator. If we multiply both sides of this relation by x to the 2, we have x2 times by 1 minus 100 over x to the 2. If we multiply right side of the equation by x2, because it's 0, it's again 0. x2 times by 1 is x to the 2, and x to the 2 times by 100 over x to the 2, x2 and x2 cancel each other and negative 100 remains, equal 0. From this equation, x to the 2 is 100 and x would be positive 10 and negative 10. Because in the question we are looking for two positive numbers, we reject negative 10 and we only accept 10 as our answer. Now if we plug in 10 in this relation that here we have between y and x, y would be 100 over 10. 100 over 10 is 10. So y is also 10. So the two positive numbers whose product is 100 and whose sum is minimum are 10 and 10. And the sum of those numbers is 10 plus 10, which is 20. If you want to prove that these answers for x and y shows the minimum of the sum, you can use the first derivative test or second derivative test. Here I use the second derivative test. For the second derivative test, we have to find s double prime. We have to find the derivative of s prime again with respect to x. We have to find the derivative of 1 minus 100 over x to the 2. Derivative of 1 is 0 minus. For finding the derivative of 100 over x2, we can use quotient rule, or we can bring x2 to the top and write it as 100 times x to the negative 2. And now with the power rule, the derivative is negative 200 x to the negative 3, which we can rewrite it as negative 200 over x to the 3. So the derivative of 100 over x2 is negative 200 over x to the 3, which if we simplify the negative with the negative, the s double prime would be 200 over x to the 3. Now if we plug in our critical number, which was 10, in s double prime of 10 would be 200 over 10 to the power of 3. Because s double prime is positive, we know that from second derivative test, if s double prime will be positive at the critical point, that point shows the minimum of the function. So in this way, we proved that this critical point is the minimum point for the function. Let's do another example. A farmer has 3,600 meters of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Let's suppose this is the river and this is the field that we want to fence it. And the total fence that we have is 3,600 meters. We want to fence such that the area of the field will be maximum. The field is a rectangle. Let's name this side of the field to be X and the other side to be Y. Area of this field is X times Y. We want to maximize this expression. But what is our constraint in this question? Note that in total we have 3600 meters of fence. So x plus 2y, note that the two sides are y. We have two sides with the length of y and one side with the length of x. The total of x plus y plus another y should be 3600. So the constraint that we have is that x plus 2y should be 3600. So here we want to maximize area with this constraint. The area is in terms of two variables x and y. First we have to try to rewrite it in terms of one variable. And to do so, again, we start from our constraint that here we have. We know that the relation between x and y is that x plus 2y is 3600. This time I prefer to find x in terms of y, because if you want to isolate for y, you get a fraction. From this relation, isolating for x is easier than isolating for y, so we prefer to find x in terms of y. From our constraint, x would be 3600 minus 2y. If we use our constraint and we replace x in the area with 3600 minus 2y times by y, the area would be 3600y minus 2y squared. Now for maximizing the area, we have to find the critical points. And for finding the critical points, as usual, we have to take derivative of the function. Derivative of 3600y is 3600, and derivative of 2y squared is 4y. If we set the derivative equal 0 for finding the critical points, y is 900. For finding the length of the other side of the field, we can plug in 900 in this relation to find x. And x would be 3600 minus 2 times 900. 2 times 900 is 1800, 3600 minus 1800 is 1800 meter. So these are the dimensions of the field that maximize the area of the field. To prove that these numbers maximize the area of the field, again we can use first derivative test or second derivative test. Here for this example, I show you both of the methods. Let us start with the first derivative test. Draw the number line here. 900 is the critical point. If we use a test point for finding the sign of derivative for values less than 900, for example, we can use 0 for y. If we plug in 0 for y in the derivative, 4 times 0 is 0. 3600 minus 0 would be positive. So derivative is positive for values less than 900. And if we use another test point for values bigger than 900, like 1000, 4 times 1000 would be 4000. 3600 minus 4000 is negative 400. So the sign in the right side would be negative. Because derivative is positive for values less than 900, and after 900 derivative is negative, this shows that 900 is the maximum point for the function. This is how we can use first derivative test to prove that this critical point is maximum point. Now let me show you how we can use second derivative test to prove that 900 as a critical point is maximum point, makes the function maximum. First, we have to find a double prime, second derivative of a. Derivative of 3600 is 0 and derivative of negative 4y is negative 4, which if we simplify it, it's negative 4. Because second derivative is always negative, this shows that it can have only maximum. Because when second derivative is negative, it shows that the function is always concave down, and when a function is concave down, it can have only maximum point. This is another way that we can prove that the critical point is a maximum point. Let's do another example. Design an open box having a square base and a total surface area of 108 square inches. What dimensions will produce a box with maximum volume? Suppose this is our box. Note that this is an open box. So the top of the box is opened. And so the material that we use is only for the bottom and the side of the box. And the base of the box is a square. So we can suppose that these two are equal to x, and the height of the box is a different value. It can be, let's name it y. The constraint that here we have is that the total surface area is 108 square inches. So let's find the total surface area of this box. Area of the bottom of this box, or area of the base of this box, is x to the 2, because x times x is x to the 2. This box has 4 sides or 4 walls. That area of each wall or side is x times y. And because it has 4 walls, in total it is 4xy. So x2 plus 4xy is the total surface area of this box. Again, note that this box is an open box. And so we do not consider the area of the top of the box. And this total should be 108. Based on this constraint, we want to find the values of x and y that maximize the volume of the box. Let's suppose the volume of this box is V. The volume would be the area of the base of the box, which is x to the 2, times by height of the box, which we named it y. So we want to maximize x2 times y with this constraint. As usual, we have to try to rewrite our function in terms of one variable. Right now, the volume is in terms of two variables, x and y. We have to rewrite it in terms of one variable. If we use our constraint and isolate this relation for y, if we move x to the 2 to the other side of the equation, we have 4xy equals 108 minus x to the 2. And if we divide both sides by 4x, y would be 108 minus x2 over 4x. Now if we use this relation, volume would be x2 times 108 minus x2 over 4x. Note that we can cancel 1x from the denominator with 1x from numerator, and then volume would be x times 108 minus x to the 2 over 4. If we multiply x in the bracket, volume is 108x minus x to the power of 3 all over 4. Note that you can rewrite your volume in the form of 1/4 of 108x minus x to the 3. Now for finding the value of x that maximize the volume, we have to find the critical points. V prime is 1/4 is the coefficient. We write the coefficient and we take derivative of the inside of the bracket. Derivative of 108x is 108, and derivative of x to the 3 is 3x to the 2. For finding the critical points, we have to set our derivative equal 0. So 1/4 times 108 minus 3x to the 2 equal 0. Which from this equation, the expression inside of the bracket should be 0. So 108 minus 3x to the 2 equals 0. If we move 108 to the other side of the equation, we have negative 108. And if we divide both sides by negative 3, finally x to the 2 would be equal to 36, which if we take a square root from both sides, x is 6 and negative 6. Because x is the length of this, because x shows the dimension of the box, x cannot be negative. So we reject negative 6 and we only accept 6 as our answer. Now if we use this value of x and we plug in this value in this relation, we can find the value of y. Y equals 108 minus x to the 2. X is 6, 6 to the 2 is 36, all over 4 times 6 is 24. 108 minus 36 is 72. 72 over 24 is 3. And this shows the height of the box. If we want to prove that these values make the volume of the box maximum, we can use again first derivative test or second derivative test. Here I use the second derivative test. So first I have to find v double prime, second derivative of the function. Because v prime was 1/4 times 108 minus 3x to the 2, v double prime would be, again we have to write 1/4 because it's a coefficient. We write the coefficient and we take the derivative of the expression inside of the bracket. We don't need to use the product rule. We write the coefficient and we just take the derivative of the expression. Derivative of 108 is 0 and derivative of 3x to the 2 is 6x. which you can rewrite it as negative 6x over 4. Now if we plug in our critical point, which was 6, in v double prime at 6 is negative 6 times 6 over 4. Negative 6 times 6 is negative 36 over 4 would be negative 9. Because second derivative at the critical point is negative, it shows that the critical point is the maximum point for the function. Now let's work on this question. A cylindrical can is to be made to hold 1 liter of liquid. Find the dimensions that will minimize the cost of the metal to make the can. So we want to make a can that can hold 1 liter of liquid. First of all, note that 1 liter is actually 1000 centimeter cubed. We want to find the dimensions that minimize the cost of the metal. For minimizing the cost of the metal, actually we have to minimize the surface area of this cylindrical can. Suppose this is a can with volume 1000 centimeter cubed. We know in general, volume of a cylinder is area of the base times height. Because the base is a circle, area of the base is pi r squared. And if we suppose the height of the can to be h, pi r squared times h should be 1000 centimeter cubed. This is our constraint. We want to minimize the surface area of this can. Surface area of a can is area of the bottom and the top of the can. The bottom of the can is a circle and the top of the can is also a circle. So we have to find the area of each circle and we have to double it because it has the bottom and the top. So the total area of the bottom and the top of the can is 2 pi r squared. The area of a circle is pi r squared. We have 2 circles in the bottom and the top of the can, so 2 pi r squared. The lateral area of the can, the area of the side of the can, is 2 pi r, the perimeter of the circle, times by height of the can. So we want to minimize this function with this constraint. Note that the function s has 2 variables, r and h, and as usual we have to try to rewrite it in terms of 1 variable. From our constraint, easily we can find h in terms of r. If we divide both sides of the relation by pi r squared, h would be 1000 over pi r squared. So s is 2 pi r squared plus 2 pi r times by 1000 over pi r squared. If we simplify pi from the top with pi from the bottom and 1 r from the top with 1 r from the bottom, s would be 2 pi r squared plus 2000 over r. Note that 2 times by 1000 here is 2000. Pi from the top and pi from the bottom cancels, and 1r from the top with 1r from the bottom cancels. And we get to this expression for s. Now, for finding the value of the r that makes s minimum, we have to find the critical points of the function. S prime would be 4 pi r. Derivative of 2 pi r squared with the power rule is 4 pi r. Plus, we can find derivative of 2000 over r with the quotient rule, or instead of using quotient rule, we can write this as 2000 times r to the -1, and then we can use power rule. If we use power rule, -1 multiplies by 2000, it becomes -2000 times by r to the power of -1 minus 1, which is -2. And we can rewrite this as -2000 over r squared. So derivative of 2000 over r is -2000 over r squared. For finding the critical points, we have to set s prime equals 0. So 4 pi r minus 2000 over r squared equals 0. For solving this equation, we can do a common denominator, or we can multiply both sides of this relation by r squared to get rid of r squared from the denominator. Here I do a common denominator. R squared is the common denominator, and in the top we get 4 pi r to the 3 minus 2000 equals 0. This fraction equals 0 when the numerator will be 0. So we don't care about the denominator. We ignore the denominator and we just set the numerator equals 0. And so 4 pi r to the 3 minus 2000 equals 0. From this equation, r to the 3 is 2000 over 4 pi, which if we simplify 2000 from the top with 4 from the bottom, it becomes 500 over pi. And from this, r is cube root of 500 over pi. So this is the radius that makes the cost of making this can minimum. If you want to find the height of this can, you can plug in this value here in this relation to find the height of the can. But how we can prove that this critical point is the minimum point for the function? We can use the first derivative test or second derivative test. Here I prefer to use the second derivative test to prove that this point is the minimum point for the function. So first we have to find s double prime. And for finding s double prime, we have to find derivative of this expression. Derivative of 4 pi r is 4 pi minus, for finding derivative of 2000 over r squared, we can rewrite 2000 over r squared as 2000 times r to the -2, and from the power rule, derivative would be -4000 times r to the -3, which actually is negative 4000 over r to the 3. So this is the derivative of 2000 over r squared, which if we simplify negative with negative, we get 4 pi plus 4000 over r squared. Because s double prime at the critical point, which is 500 over pi, is positive, it shows that the critical point is minimum. Also, you can use the first derivative test to prove that the critical point is minimum point for the function. Actually, let me show you how you can use first derivative test to prove that the critical point is minimum point. Let's draw a number line here. The critical point is cube root of 500 over pi. If we want to find the sign of s prime for values less than cube root of 500 over pi, we can use a test point less than this value. For example, 1 is a number that is less than the critical point. If we plug in 1 for r here and here, s prime would be 4 pi minus 2000 over 1. 4 pi minus 2000 is negative. And if we use a test point greater than this value, easily we can see that s prime is positive after the critical point. And it shows that the critical point is the minimum point of the function. Find the point on the parabola y equals 1/2 x to the 2 that is closest to the point 4, 1. First, let's draw a picture for this question. The graph of the function y equals 1/2 x to the 2 and the point 4, 1, 1, 2, 3, 4 is somewhere here. We want to find the coordinate of a point that lies on this graph that is closest to this fixed point. We want to know the coordinate of that point. Before we start, let me remind you the formula for the distance between 2 points. If we have a point like x1, y1 and another point x2, y2, the distance between these 2 points is a square root of x2 minus x1 to the 2 plus y2 minus y1 to the 2. This formula shows the distance between any 2 points. For example, if you have a point like 2, 1, another point negative 3, 4, the distance between these 2 points is minus 3 minus 2 squared plus 4 minus 1 squared. Negative 3 minus 2 is negative 5 to the 2 is 25. 4 minus 1 is 3. 3 to the 2 is 9. So the distance is a square root of 34. The coordinate of this point here is 4, 1. But we don't know the other point. But we know that that point lies on this parabola. Because we don't know the coordinate of that point, we consider that point to be x and y. Now the distance between these 2 points is a square root of x minus 4 to the 2 plus y minus 1 to the 2. So we want to minimize this expression. But as you can see, this function or this expression has two variables, x and y. And as usual, we have to try to rewrite it in terms of one variable. Note that y and x are related to each other by this equation. Y is 1/2 x to the 2. So we can replace y in terms of x. And so d is a square root of x minus 4 to the power of 2 plus 1/2 x2. We replace y with 1/2 x to the 2 minus 1 all to the 2. Now the distance is in terms of the variable x. So we have only one variable. For finding the value of x that makes this expression minimum, we have to find the critical points. But as you can see, finding the derivative of this function is a bit hard because we have a square root, and under a square root we have a relatively complicated expression. Here we can use a trick. Instead of minimizing the square root of this expression, we can minimize its square. We can minimize d to the 2, which is x minus 4 to the 2 plus 1/2 x to the 2 minus 1 all to the 2. And if you compare this expression with this expression, finding the derivative of this one is much easier compared to this one. Here I am doing both, and then we compare the results and we will see that the result is the same. So let us start with the simple one. Before we start, I name this expression f of x because this expression is in terms of x, so I name it f of x. F prime of x, the derivative of f of x would be 2 times x minus 4. Then derivative of the inside of the bracket is 1, because the derivative of x is 1, derivative of 4 is 0, so derivative of inside of the bracket is 1. And the derivative of the second expression is 2 times 1/2 x to the 2 minus 1 all to the power of 1 times by derivative of inside. Derivative of 1/2 x to the 2 is x, because the derivative of x2 is 2x, 2x times 1/2 is x, and derivative of negative 1 is 0. So derivative of inside is x. If we simplify this expression, we get 2x minus 8 plus, if we multiply 2 in this bracket, we get x2 minus 2 times by x, which if we simplify it more, we have 2x minus 8 plus x to the 3 minus 2x, which finally, if we cancel 2x with 2x, we get x to the 3 minus 8. Now if we set f prime of x equal 0 for finding the critical point, x to the 3 is 8 and x is 2. So this is the critical point that we get for the square of the d, not the d itself. Now let's find the critical point for the distance, the original expression. We can write it as x minus 4 all to the 2 plus 1/2 x2 minus 1 to the 2 all to the power of 1/2. Derivative is bring the power down, write the expression inside of the bracket, to the power of 1/2 minus 1, 1/2 minus 1 is negative 1/2. And then multiplied by derivative of inside of the bracket, derivative of this expression. Derivative of inside of the bracket is 2 times x minus 4 plus 2 times 1/2 x2 minus 1 to the power of 1 times by derivative of inside, which is x. If you remember, this part is exactly the same expression that we get from the other derivative. Now we have to set d prime equal to 0 for finding the critical point. But note that because this part of the expression has power negative, so it goes to the denominator and it cannot be 0. So the part that we have to actually set equal to 0 is only this part of the derivative. And it is exactly what we did in the other derivative. So if we ignore this part and we just focus on the other part, we have 2x minus 8 plus x to the 2 minus 2 times by x equals 0. And if we simplify this, we have 2x minus 8 plus x to the 3 minus 2x equals 0. Which if we simplify, we have x to the 3 minus 8 equals 0. And finally, x is 2. As you can see, the result is the same and it doesn't matter. You can find the critical point for d, or you can find the critical point for d squared. Because x equals 2, y equals 1/2 times x to the 2, and x is 2 times 2 to the 2. 2 to the 2 is 4 times 1/2 is 2. So the coordinate of the point that is closest to the given point is 2, 2. So the coordinate of this point that we were looking for is 2 and 2. But how we can prove that this point is the closest point, or the distance is minimum? Again, as usual, we can use first derivative test or second derivative test. If we use first derivative test to prove that this point is the closest point, or the point that minimizes the distance, if we draw a number line and we put 2 here, if we use a test point like 1 or 0 in the derivative, easily you can see that derivative is negative for values less than 2, and derivative is positive for values greater than 2. And this proves that this point is the minimum point. Let's do another example. An open top box is to be made by cutting small congruent squares from the corners of a 12 cm by 12 cm sheet and bending up the sides. How large should the squares cut from the corners be to make the box hold as much as possible? So we have a sheet like this in a square form that each side is 12 by 12, and we want to cut squares from the corners such that when we bend or we fold the sides, we can make a box with the maximum volume. So we want to cut, say, x centimeter from here, x centimeter from here, and similarly from each corner we cut x, and then we start folding from here, here, and here, and we make an open box. We want the volume of that box will be maximum. We know that volume of the box is length times width times height. Because the total length of the box is 12 centimeter, when we cut x centimeter from the left and x centimeter from the right side of the sheet, the length of the box would be 12 minus 2x. And similarly, the width of the box, the width of the bottom of the box would be 12 minus 2x. And the height of the box would be x. When we fold these parts, here, here, and here, this part will be the height of the box, and the height would be x. So we want to maximize this function, 12 minus 2x times 12 minus 2x times x. If we multiply the expressions in the bracket, we get 144 minus 48x plus 4x2. And if we multiply x in the bracket, volume would be 144x minus 48x2 plus 4x to the 3. For finding the value of x that maximize this function, maximize the volume, we have to find the critical points. V prime is 144 minus 96x plus 12x2. For finding the critical points, we have to set V prime equal 0. So 12x to the 2 minus 96x plus 144 equal 0. If we pull out 12, we get x2 minus 8x plus 12 equal 0. Note that we can factor this as x minus 2 times by x minus 6. So x is 2 and x is 6. Between these two values, we only accept x equals 2 and we reject x equals 6. Because if x will be 6, 12 minus 2 times 6, 12 minus 12 would be 0, and the length of the box will be 0, which doesn't make sense. So we only accept 2 as our answer. Note that 2 will be the height of the box, and the length of the box is 12 minus 2 times 2, which is 8, and the width of the box also will be 8 centimeter. If we want to prove that x equals 2 makes the volume maximum, we can use first derivative test or second derivative test. Here I show you both methods. Let's draw a number line here. The critical points are 2 and 6, and we want to prove that 2 makes the volume maximum. If we use a test point like 0 for this region, and we plug in 0 in V prime at 0 would be positive. If we use a test point between 2 and 6 like 3, 4, and we plug in for x, V prime is negative. And finally, if we use a test point after 6 like 7, 8, any number greater than 6, you will see that V prime would be positive. So this shows the sign of V prime. Because V prime changes from positive to negative around 2, this shows that point 2 is the maximum point of the function. Another way that we can prove that 2 is the maximum point is to use second derivative test. V double prime is 0, derivative of 144 is 0, minus derivative of 96x is 96, and derivative of 12x to the 2 is 24x. Now if we plug in the critical point 2 in V double prime, it equals to negative 96 plus 24 times 2, which equals negative 48. Because V double prime is negative, it shows that this critical point is a point that maximizes the function.